Hello guys, and welcome once again to the KNS Degree Biotech Hub. In this tutorial, we'll be carrying out three main activities. The first one is going to be um, how to perform one-way Anova, and then we'll head on to performing pairwise comparison tests, specifically two keys, okay, test, and then we'll see how to write all the results that will be displayed in the console onto a text file. Okay, so the data I would be using for this tutorial is a Google Sheets file. Okay, and as such we would have to authenticate, okay, because it's a Google Sheets Hello guys, and welcome once again to the KNEST Agri Biotech Hub. In this tutorial, we'll carry out three key things. We'll see how to perform a one-way Anova. We'll see how to perform a pairwise comparison test. Basically, it will be the two keys, okay? And then we'll see how to write all the results that will be displayed in the console as text files, okay? All right, so the data I would use in this tutorial is in Google Sheets, okay, and this is the link to that data, okay. If you want to see it, we could browse. A minute, sorry. So let's have a look at what is in the data, okay. So to do that, we'll use the function browse URL. So we'll browse URL, and then we'll paste the link here, okay. First, so let me just run this link into the object called link and then browse it, okay. So yeah, so this is how it looks like, okay. This is the data, and we would want to read this data into R, okay. We want to read this data into R. So before reading the data into R, we'll first have to authenticate. So from the package called Google Sheets 4, I am importing the Google Sheets authentication function, okay. So once I run it, it asks me, okay, it's requesting access to your Google account, so give a new authentication process. If it's a new authentication process, fine, but if you want to use an existing account, you can. So I'm going to use my existing account, and once I'm done with that, from Google Sheets 4, okay, I can now read the data embedded in this link, okay. So from Google Sheets 4 package, I am importing read sheet link, okay, read sheet. And then inside the read sheet, what I did here was that the link to the sheet, okay, I just had to put it here, okay. So now when I run this and I print, let's say, data, okay, when I print data, you would see it here, okay. We have treatment, rep 1, rep 2, rep 3, just as you saw in the Google Sheets file, okay. Now this is what we want to analyze, okay. This is what we'll be doing today, okay. Now before um before carrying out an analysis in R, with such a data like this, I would assume, let's say, this data is to see the treatment effects, the varying concentrations of certain treatments on, let's say, plant height, okay. And for treatment 1, which is 7.5 milligram per liter, it have 3 reps, okay. And this is basically a CRD experiment, okay. Good. So here, before, like I said, before performing an analysis, the data you see here, you can all see here is a Y format data, okay, a Y format data. But in R, before doing any analysis as such, you need to convert the data to a long format data. That is more suitable. A wide format data will be more suitable for the reader or the one who is collecting the data. Yeah, but then a long format data is most suitable when carrying out an analysis. And you can read more on wide format data and data and long format data. Okay, so here what we're going to do is that we're going to convert this to a long format data, and you will see how the long format data looks like after we are done with this. Okay, so here we'll convert data to long format. Okay, good. We'll convert the data to long format. Now there is sorry, there is a package that carries a function that would help us to do this. Okay, and because you are trying to tidy the data, the package name is tidyr. Okay, tidyr. So we're going to load this package. So library tidyr. Okay, and we'll run. Okay, now that we have run this, okay, we can now head to converting the data from a wide format to a long format. Okay, now we're going to make use of the function in tidyr. We're going to make use of the function pivot longer. Okay, pivot longer, and you could see the first argument is data. And what is our data object? It is what? Data, right? This is our data object. Okay, so it's data, right? Good. Then the next argument says columns. Okay, so here in our sheet, okay, we have these columns. Okay, we have these columns. Okay, treatment, rep 1, rep 2, rep 3. But what we're going to convert to long format, it's going to depend much on the columns designated as reps. Okay, so here we're going to say any column that starts with rep, okay, that is what we want to collate together and then perform or have a long format data from. Is that okay? So we are going to say any column that starts with what? Rep, right? Any column that starts with rep, sorry, rep, we should pull we are going to concern, or we are going to focus much on those ones. Those ones are going to be the pillars for which the long format data will be generated. Now the next argument is codes vary. Here we don't have any columns that are varying, so we're going to head to the names too. So it means that when we get these columns, okay, these rep columns, okay, and they have been obtained, we need to store them in a particular column. Okay, so what column name will you allocate to those columns? Okay, those columns that you are now coming to convert as a long format. So what column name will you give to it? So we'll give reps. Okay, reps, it will be reps. We'll give the names to reps. Picture it this way: we are taking all these column names, okay, and then we are assigning it to a unique column called reps. Okay, and then the next is the value. Okay, as you can see, each column, which is a rep 1, rep 2, rep 3, has values. Okay, they all have values. And I said for this data, we'll consider it as an experiment where one was trying to see the effect of treatment on plant height. Okay, these treatments on plant height. So these values are plant height scores or plant height data. So we're just going to say assign the values to plant height. Okay, assign the values to plant height. And if I should just run this, you will see that we now have a long format. Okay, so there are differences. If you look at the wide format, okay, it's wide. If you look at the long format, it's long. Okay, yeah, I don't want to dive much into those things. You can go and read about it. All right, so now here we have run this, but we haven't stored it in an object. Okay, so we're going to create an object called data long, because that is, yeah, it's a long format data. So data long, okay, here. So now when I print data long, we now have an object designated for the long format data. Is that okay? Good. This is the way. Okay, now we have transformed our data to a long format. We can go ahead to perform our analysis of variance. Okay, one-way Anova. So one-way Anova, performing a one-way Anova on this long format data long, right? Data long. All right, but then take note, Anova has assumptions, right? The assumptions of Anova is that one, the data should be what normally normally distributed. Okay, it should be normally distributed, or it should, or we'll say normality. Okay, and the second assumption is that it has to, the data must have a homogeneous variation. Okay, so homogeneity, I'll put it here as homogeneity, oh sorry, homogeneity of variance, right? Good. Now for the normality, we would use, to test if the data is normally distributed, we'll use Shapiro test, and to test if the variance are homogeneous, okay, we would use the Levene's test. Okay, Levene's test. We'll carry out a Levene's test to do that. So if we check these two assumptions and our data does not meet it, then it means that we'll have to go ahead and transform our data. Okay, but for this tutorial, okay, you don't worry, let's just go ahead. So let's test. So first, test if it's normally distributed, right? Test of normality. Okay, so I said we're going to use Shapiro. Okay, so we're going to use a Shapiro test, and yeah, so the argument we are expected to have here is the column for the values. Okay, the values, okay, the dependent values. Okay, here we have independent. Our treatment is our independent value, but this is our dependent value, right? So it's going to be the dependent value. Is that okay? All right, so to do that, we could have data long, and then we subset the column for the dependent values, which is plant height, right? So now if we run this, this is the results we are having. Okay, and this from the Shapiro and Wilks test. Okay, if you have a p-value that is greater than 0.05, okay, it means that the data is normally distributed. Okay, but if the p-value is less than 0.05, it's not normally distributed. Okay, right. So here we have tested normality, and we have seen that our p-value is what, greater than 0.05, right? So let's store this in an object called Shapiro, I'll say sharp results, right? Sharp results. Okay, sharp results. So here we have it again. I think I have to be creating the objects first before doing all those things. Now, this is the first assumption for performing Anova has been met, right? So we move on to the next assumption. Okay, we move on to the next assumption, which is homogeneity, right? Homogeneity. And for homogeneity, we're going to use a function Levene's test in a package called car. So library, we're going to load the package called car, and that is it. Yeah. Now, if you pay close attention, anytime when I had to subset the plant height, okay, I make use of the dollar sign, right? But we could, attach the data to the environment such that arrow will now pull out the respective column names. We won't have to really be using the dollar sign or square bracket to subset anything, okay? Once we attach it to the environment, okay, we can automatically access the column names, okay, the columns, sorry, we could automatically access the columns without having to use the dollar sign. So how do we attach? It's basically we calling the attach function and then inputting what we want to attach. We want to attach data long, right? So now it has been attached. So if I want plant height data, I could just type plant height and you see it here, and when I run, I have it. Okay, if I want treatment, I could just type treatment, sorry, I could just type treatment and I run, it is here. Do you see that? Yeah, if it is reps, I could go ahead, reps, okay, and I have it here, simple. So the best thing, sometimes I would advise that you just attach it to the environment, okay, good. So here we attached data long. I like commenting a lot, data long to the environment, okay, good. So to perform a Levin's test, this is basically what we need to do. We need to call the Levin's test function, okay, and in the Levin's test function we'll write our module, okay, our module. So we'll first have to specify, okay, what our independent variable is, what our dependent variable is, and what our data is, okay. So here our dependent variable is going to be its plant height. It's going to be its plant height, okay, and we use a tilde symbol or sign, and we call our independent variable. Our independent variable is treatment, right? Good. And what is our data? Our data is data long, okay. So this is the formula we're using, and this is our data, right? So our dependent variable against our independent variable, and we want to see if it is also the variance there is what, homogeneous. So when we run, we have a p-value which is 0.9089, okay. This means that it's greater than 0.05, hence the data is what, normally distributed. Supposing the data was not normally distributed, we would have to transform, of course, and maybe in another video I would try a data that has not that is not normally distributed, or that doesn't meet the assumptions of Anova, and we'll see how we can transform it, okay. One package or one function we could use is box course, which is in the mass package, okay, good. So here I'll say Levin's results, right? I'll say just say Lev's results. I'm creating the object to store that, so Lev's results, and we have this, right? So if we should print Lev's results, we have this, right? Good. So since our data is normally distributed, or and the variance is also homogeneous, which meets the assumptions of ANOVA, we can now go ahead to perform our analysis one way ANOVA, okay. So now to ANOVA, this is to ANOVA. Sorry guys that I'm rushing. I want to make sure the video is as short as possible, so I'm very sorry if I'm rushing, but then maybe you could slow me down, okay, when you are watching, and then at least the practice, okay, good. So to perform ANOVA, we're going to make use of the function AOV. Okay, AOV is basically what we use in performing the function we call when we want to perform Anova. Okay, so when I hit the tab key, it says formula, and the next is data, right? So what is the formula? The formula is basically this model we have here. We have our dependent variable against what? Independent variable. Okay, we want to see how the dependent variable depends on the independent variable or interacts with the independent variable, however you want to see it. So I'm just going to copy this. I don't want to write the whole of this again, so I'm just going to copy and paste it here. Then for the data, I'll have to specify is data what? Long, right? Note I haven't created an object to store this result, right? I'm just going to run this for you guys to see. Then later I would create an object to store it. Okay, so if I should run this, this is what you have, a lot of gibberish, right? And people, you would ask, where is the p-value, where is this, where is that? Okay, so once you perform the analysis this way, okay, once you perform the analysis this way and you want to see you want to clearly understand what has been done, you have to summarize. So use a summary function. So I'm piping this into that, and this is the pipe operator for that. Okay, so I'm taking all the results that will be generated here and putting it in the summary function. Now if I should run this, you will see that you can now appreciate what you saw here. You can now appreciate it better here. So here we have our p-value to be what? 0.0247, and since it is less than 0.05, it means that it is statistically what? Significant, meaning that there are some components of the treatment that had effects on plant height, right? Good. So now let's store this in an object, right? Let's store this in an object. So the object I'm going to store this in is going to be Anova result. Okay, I'm storing it in an object called Anova result. Now for us to see which treatments, okay, are significant, we'll have to perform a pairwise comparison test. And to perform that pairwise comparison test, I said we're going to use the two keys, right? Two keys. So with two keys, we have to just call the two keys function, and then the Anova model. Okay, here, observe the Anova model we have here. We just have to copy it and paste it here. Okay, you don't, please don't after running this, don't come and take the object here and put it here. It won't work except you take away the summary function. Okay, except you take away the summary function, sorry. But since we have already run this, okay, and we've seen how it looks like and stored in an object, and I want you guys to understand what is being done here. That is why I copied the model, the Anova model, and placed it in the two keys function. Okay, so now let's run this, and we have this here. Okay, so for two keys, our p-values, if we want to see that they are significant, if we want to see those treatments that are significant, we expect p-values to be less than 0.05. And if you observe, this and that, okay, are the significant scores. Okay, and you can go ahead to interpret this results. Okay, sorry, you can go ahead to interpret this results. Okay, between a comparison between 12 milligram per liter and 10 milligram per liter. Okay, the difference is negative 3.97 with a p-value of this, meaning that the 12.5 milligram per liter treatment had much lower effect. Okay, the effect was a bit lower. Okay, and if you look at this, though it had a significant effect, the effect was lower. If you look at this, 7.5 to 12.5, we had a positive difference, which means that 7.5, okay, had a huge effect on plant height, right? But 7.5 and 10 milligram per liter, the interaction between this had no yielded nothing. Okay, the p-value is greater than 0.05. Okay, but you can go ahead and do your interpretations. Okay, good. So we perform our two keys, we perform Anova. So let's keep this in an object called two keys results, right? Two keys results, and we have that there. So now uh, we have completed the analysis. We've performed all the activities except writing the results as a text file, right? Good. So to write the results as a text file, we would make use of the sync function, okay? A sync function. And it's going to be two syncs, sync 1 and sync 2, okay? So you open 1 and then you close 1, right? And inside the sync, the first sync, you're going to give the file name to your results. So I'm going to say one way in quotes, so one way Anova results, then the extension, so .txt, right? Good. So in here, okay, in here you're going to enter the results that was displayed in the console that you, the user, you, the analyzer or the analyst, wants to have. Okay, instead of, let's say, copying this, going to paste it in maybe Microsoft sorry, Microsoft Word, okay, or maybe taking a screenshot or whatever it is, you could just use the sync function to perform this analysis. Sorry, to write this text file. Oh, what is happening? sorry guys, sorry. Yeah. So good. So let's write our results out. Okay. So the first result we're going to write is the, let's say, the data long. Okay, so we're going to cut some, let's say, a brief information, okay, to you, the user or the analyst. Okay, so this, I could say this is the data, or I could say data used. Okay, and then I could, you know, shift it or give a paragraph. Okay, so that is it here. Good. Then data used, and then I'll just print what? Data long. Okay, if I should just run this and this for you to see, this is how it appears. Okay, this is how it's going to appear. Data used, and then we have treatment, or I can just take this, give a semicolon and paste this here and then run, so that you guys will appreciate it better. So if you look at it in the text file, you're going to see something like this: data used, and then this. Is that okay? Data used, and then we have this, the data. Okay, good. Now the next thing we're going to deal with is the Shapiro test, right? And which is Shapiro result. So let's write something a bit. We're going to say we're going to introduce a paragraph, or we're going to skip a line. Okay, we just skip one line. Okay, and then we'll say Shapiro results, or normality results. We say normality results. Okay, and then we skip one line as well, and we now print. We go ahead to print the normality results. So print Shapiro results. Okay, good. So we're done with this. Then we have Levin's test as well. Don't worry, just observe what I'm doing, and once the results is out, once the results is displayed, you have a better understanding of it. Okay, I'm just trying to organize my results on the text file. That is what I'm trying to do here at the moment. Okay, so um the next is Levin's result. So I'm going to say this is the homogeneity of variance, right? Homogeneity of variance, and then I'll just leave a line. I don't want it to be clustered. Then I have print, okay, print Levin's test, right? It was Levin's results. Yeah, it was Levin's results. So we have this here. Good. Now, after doing that, we head to our Anova results. So the same thing, we're going to cut and give a comment. Okay, we'll say this is one-way Anova results, and we just leave a line, and then we print. Okay, we print Anova results. Good. Then finally, the end of the tutorial is um, two keys, right? So we're going to leave a line, skip a line. We're going to skip a line, and say two keys results. Two keys results. I don't know what's happening to me today. Yeah, but sorry. I'm so sorry, guys. Yeah. So two keys results, and then we have this. Okay, and then we're going to print the two keys results. Okay, good. So we are done. Okay, I'll just bring this a bit. So we first opened sync, we've closed, and then we have this, right? Good. So if you need to set your working directory to have your results into that particular directory, then you could do that. You could set directory. Okay, yeah, so we'll just run everything. Okay, we'll just run everything from the start of the sync to the end of the sync. So run, and end the sync, and then let's get our directory. Okay, my directory is the pan genome breeder directory. So it means if I should head there, or if I should just list the files there, I could get it, right? I could list the files in my directory, and you see that we have one-way Anova results txt. Let's try and open that folder and see. Desktop, pan genome breeder. Yeah, here. And I have this, right? So as you can see, your results has been written out for you very well. Okay, so data used, this normality results, that. Okay, everything has been converted in a text file, and you can go ahead and make your interpretations to this data. Yeah, so thank you very much for joining this session as well. If you have any comments or issues, you could leave it in the comment section for us.